Well, welcome to the August program meeting of the San Diego Astronomy Association. This time we're talking about one of our internal activities. This is really the reinvigoration, almost the rebirth of our astro imaging special interest group that has been strong off and on, and David Wood has breathed new life into it. And it is off and running. So I thought we would dedicate this particular program meeting to ASIG type topics, and maybe encourage people to get involved. Okay, I'm supposed to go to the next slide, and it didn't advance. And by the way, this is my image, since I'm not going to talk about deep sky imaging. I just happened to throw out one of my own. That's M81 and M82, taken with an ASI one-shot color camera and a TeleVue 4-inch refractor. And it did not advance. Oh, I love it. I always talk about the calendar. We were discussing we have West Sycamore this Friday. The question is the star party at the SPIE convention. The SPIE is the International Society for Optics and Photonics. About roughly 10 years ago, they asked us to bring telescopes to their welcome reception on the first full day of the convention. Turned out, they had this affair down at the convention center, drinks and munchies and everything. Nobody showed up. When SDAA started bringing telescopes, it became a big deal. So we've invited ever since. The ASIG group next Wednesday, depending on the status of the storm, will meet in David Woods' cul-de-sac for a demonstration by a couple of Keystone astronomers about setting up their equipment, getting the guiding work, talking about options and so forth, and maybe even getting an image or two. All the rest are kind of a routine schedule. Notice at toward the end of September, we're back at Mount Helix Park. It does not advance. I put in a slide as a placeholder. I didn't go to the Julian Starfest. Does anybody want to talk about how it went and, compare it to years past? I'll turn the floor over to anyone who wants to talk.
Ken, I was there. I know Bob Roth is in the meeting. He was there. I'm not sure who else. I believe Dennis was there. This was a huge crowd. It was probably the biggest crowd I've ever seen at JSF. And it was a great crowd. Everybody was excited about the Perseid meteor shower. I suspect that there was a lot of social media encouragement about finding someplace to go, because we had a huge number of people that were not astronomers showed up, and they had their blankets, their beach chairs. They plopped down anywhere that was comfortable and observed the meteor showers for hours, and occasionally came over and found out that there were telescopes here and that we were astronomers. But many of the people we talked to were up there primarily for the meteor shower. It was fortunate that the Perseids did a great job of entertaining us. We had lots of good stuff to look at. And so that was wonderful. We hear all the oohs and ahs that went across the whole grounds every time a bright meteor went by. And it was kind of a good, exciting time. I had a lot of fun. Anyway, it was pretty good. We had decent weather. I was there Thursday night, it was foggy. Friday night was passable. Saturday night was really good. And we had some clouds come in maybe late, but basically it was clear and a good night for observing. So big crowd, lots of fun, got some pictures, saw the sky, and that was about it.
And I know you had a good talk because Doug Leonard is super. And he was talking about Betelgeuse and when it's going to explode.
Unfortunately, I missed that. I was tasked with many duties during the weekend, so I didn't have a chance to participate in all those things, but I heard lots of good stuff.
Yes, he gave us an exact date, year, date, hour, minute, second, nanosecond, etc.
Oh,
The problem is I forget what it is.
was there an error bar on this?
A slight error bar. He would be absolutely surprised if it did not happen within the next million years. He would be not surprised at all if it happened within 10,000, I'm sorry, 100,000 years. Other than that, he says, well, it's an astronomical soon. Oh, I walked over on Saturday evening before it got too dark, and walked over to the main field, and we had campers all the way up to the end of the field. We had a huge number of campers there, more than I've seen before.
Wow. That's always pretty magical.
And I don't think all the motorhomes came or RVs came that were scheduled or signed up to come. So spaces were filled in with tent campers where we would normally have motorhomes and such. So it was packed.
Well, that's good. Sounds like a great event. Kudos to all of the people who made it happen, and to SDAA for pulling it off one more time.
Yes.
Yeah.
Okay,
A lot of the campers were saying that they will be back again.
That's good. You know, it is a neat event, and the Free Star Party with all those people, really, there's something magical when you're up there with all the campers and the evening is cool and things begin to quiet down and people are excited, and it's just a great experience. Okay, I have a little bit of astronomy news, and I'm gonna click on this Caltech video in just a minute, but Caltech astronomers have discovered a white dwarf star that is two-faced. Okay, one face is composed with hydrogen and the other is helium, and they believe it's due to magnetic properties, but I think a lot of further investigation is needed. This is the principal investigator for the team, and she's going to mention a couple of things that I'll talk about in advance. One is this was discovered by the Zwicky Transient Factory, which is a combination of two telescopes at Palomar that just operate mechanically surveying the sky on a continuous automatic basis. The 48-inch surveys is the Schmidt telescope that surveys the sky every 2 nights, and the Milky Way twice in 1 night. They data link all those images up to Caltech. They're examined, you know, a comparison, you know, A to B from the time before, get with artificial intelligence, get something like, you know, 500,000 hits every night. There's a huge amount of data. The most promising get queued up to be classified rapidly by the 60-inch telescope at Palomar. And then if it passes that screen, they send it out to the 200 Keck and other telescopes, and, you know, basically tell the world. She's going to talk about Chimera on the 200-inch telescope, and this is a neat instrument. It's a very rapid imaging system. It has 2 cameras. It goes up at prime focus, and it can operate almost, you know, faster than video speeds if necessary to get detail on fast moving things like small close binary star orbits, various types of stellar emission from brown dwarfs and things like that. So that's just a little bit of a cue, but she's going to explain it very well. And when we see at the end of this video, you're going to think we need to invite her to be one of our speakers. So here she is.
Hello, my name is Ilaria and I'm a postdoc at Caltech Astronomy. With my group, we found a very strange white dwarf star. White dwarfs are the corpses of stars like our sun. And in particular, the white dwarf that we found is a double-faced white dwarf. On one side, it's made of hydrogen, and on the other side, it's made of helium. We found this very strange star thanks to the Zwicky Transient Facility at Palomar and the P200 telescope with the Chimera instrument, where we could get a light curve, which is the luminosity of the star going up and down as the star rotates. We also pointed the Keck telescope at the star to get spectra, and the spectra tells us the composition, so the hydrogen side and the helium side. Because of this very strange double-faced nature, we nicknamed the star Janus as the double-faced Roman god of transition.
So stay tuned for more about this. I'm sure we're going to hear a lot more. Oh, thank you. Well, I will turn it over to the host for the program part of the program meeting, David Wood. And with no further ado, I'm going to stop sharing and let him share and then run the meeting. Share screen. Did it stop? Yes. You're viewing David Wood's screen. Are we?
It says it's Dave Wood's screen at the top there.
Yes.
Yes, that's what it says.
Hi there.
I there?
Gotta be a lot of Zoom. Hey, welcome everybody. The Astro Imaging Special Interest Group has actually been around for quite a while. It kind of dropped off, contact kind of dropped off a bit just before, not too long before the pandemic. But it's been around for quite a long time. It kind of, the actual within side of the, there's always been, I don't say there's always been, but there has been an interest in the San Diego Astronomy Association for astro imaging. So back around 2002, 2003, a small group of people got together and tried to figure out just exactly what the heck was going on. And when I say that, the technology for astro imaging and a good portion of deep sky object imaging was based around older telescope designs, such as catadioptrics. Basically, a lot of people had, 8, 10, 12-inch Meads and Celestrons, and everybody got really excited when everybody got an Orion ED80 out there. Oh, hey, this is going to take really good pictures. The basic deal was that there was the acquisition software controlling this was all pretty primitive. Same with the processing software, and not that Photoshop was fairly primitive, but the combination of cameras that didn't work all that great and software that wasn't well defined. Bear in mind that ASCOM, which is now the standard by which all the astro imaging stuff and all the telescopes and everybody communicates with, that hadn't really been put together. So you had, various different portions of Windows. You had some really interesting looking pieces of software that came out from the camera manufacturers. And even the camera manufacturers were basically, they were using imaging chips that were really primarily made for the intelligent vision industry and the hospital industry. One of the first camera manufacturers that came out was SBIG, Santa Barbara Instrument Group. And if you were to take a look at some of those cameras, you'd look and say, huh? Because the chips were about that big, and getting any kind of image out of them at all was really difficult. So that was primarily the reason for the ASIG group to get together, because it was unlike today where you have a significant growth in camera technology, And now with the growth of and the implementation of CMOS technology that's all shared with DSLR cameras, there has been a really big boom in making astro imaging easier. I think one of the reasons we want to get ASIG back moving again is that of the new people that have joined our club, a good majority of them are interested in starting off with astrophotography. I think a lot of that has to do with the James Webb Telescope. I don't know that the Hubble telescope ever had its own Facebook page, but the official James Webb Telescope Facebook page has got something like 2 million users looking at it. So I'm not surprised that the growth of social media and sharing of the results of everybody's astro imaging stuff hasn't significantly grown the interest. So yeah, we're trying to get this back together again. Typically in the past, we've had meetings, although they weren't Zoom meetings. We actually used Google Hangouts to do a lot of our meetings. A lot of times, and I'll touch on this a little later on the meeting, but a lot of times we'd actually have some live get-togethers where we'd have a newbie night where we'd set up a bunch of telescopes where people who were having problems with things like, I don't know how to get my guiding to work, or I'd really like to figure out the best way to align my telescope, things like that. We get together in a local location, not at TDS, but someplace close here in town, and have people who are having problems mix it up with guys who've been there before. We're planning on doing that a lot more. We had talked a little bit. We've had one ASIG meeting. And one of I think probably 50% of the people that attended that meeting says, when can we get in together? I really want to see how this is put together. And because of that, we're going to do something pretty quick. We talked, everybody is kind of familiar with what you can do as far as deep sky imaging on deep sky objects. But we also have various different other types of activities that the ASIG group has always been involved with. Spectroscopy, exoplanet photometry, speckle interferometry. Those are all activities that ASIG members have had a chance to do. And they're quite willing to share those interests and hobbies with you guys. So with that, Ken, you want to go ahead and move it on to the simple stuff?
Sure. Okay. All right, yes, continue. Let me make sure. All right, here we go. So, okay, just to get us started out, the easiest thing that one can do is to take a camera and put it in a tripod and image the sky. And whereas you don't get these marvelous magnified images when stacked jillions of them together and get, incredible detail and so forth, it's kind of fun and creative. And the one thing you always have to remember about a DSLR and camera lenses is it's an engineered system. It's just going to work. It's fun. It's creative. You tend to be mobile because the whole setup, and you'll see what I used to use, is very light, and you want to be mobile because you want to be creative about anything which involves the background sky and foreground objects that you'll find yourself doing. All kinds of family members can do it. You don't have to stay out super late. And, regular photometry or photography rules, apply. Composition, perspective, but there are some specialized techniques just because the sky is so demanding. Dennis Mamana said it all. If you can see it, you can shoot it. Okay. But you're not going to need to process it in Photoshop or PixInsight. Just a couple of cautions. Camera lenses are not optimized for astronomy. And even the most expensive camera lens, I typically use a Canon 28mm f2.8. It turns out to be very good. its more expensive brethren, the 24 millimeter f 1.4 L, which costs about $1,500, is terrible because it has a lot of coma. So money doesn't necessarily buy you quality. And there is another little issue that when you get into it, if you are shooting at a low angle so that you want to get foreground objects as well as the sky, you're looking at the crappy part of the sky. So you just have to contend with that. But if you look at my little sample image on the right, you know, you can, I think that's a JSF image. It doesn't come through quite as well on the zoom, but you know, you can get the Milky Way and you can get stars and everything, and you can be quite productive. So the range would be anywhere from fisheye, and I just used the fisheye just because I had one and they're fun to play with. You can tell that's me, you know, that's a shadow of me in front of one of those Briseda sculptures down in Anza Borrego with the sky in the background. Or you can use a tracker and go higher in the sky and get a cleaner part of the sky and so forth, still wide field largely. But if you have a tracker, and they generally cost like $300 to $400 and so forth, I've played with them. Frankly, what I would recommend if you want to track is go ahead and get a small go-to mount. You'll be happier with it in the long run, but you can go the tracker route and get quite good results, maybe up to about a 200 millimeter camera lens, but I've never tried that. One thing you will do if you have foreground objects, and there's one of those neat dinosaurs, and you see the little image on the left, and we managed to catch a meteor just about ready to hit his nose. You know, again, it's not as high contrast in the zoom as you would have, but you know, you can try different colors of light. You know, there he is, kind of a brownish thing. He's naturally brown in the desert, but then you can try different colored lights to try to get more detailed or some kind of neat effect. You know, this is about as far away from science as you're going to get. This is just pure creativity with the camera and the night sky. I kind of like that one. You can see the Pleiades and the Hyades and the Orion Nebula, and you can play with a lot of compositional details like this and really have a good time. This was one of my favorites. Unfortunately, it was in the summer, as you can probably tell from the position of the Milky Way, and this beast that almost looks like a dinosaur looks like he's looking at the impactor that's going to hit and wipe them all out. And actually, this drove me to cooled cameras because it was 100 degrees in the desert and the camera was hot, and the image is a lot grainier than you would ever want. Endless variety. There's a straight rocket from Vandenberg. There's another one of those sculptures that you can play with. And the top left, I think, is Ed Rumsey walking around a Schmidt cast with his headlamp on. Generally, you can control your camera. I would get one thing you really want is a nice mount head. So this is a geared mount head that's a lot easier to control because you can ratchet it around. It has a quick release as well as the gear. The lenses for a full frame camera, you're going to be 15 millimeter to 35. 35 is a little optimistic. I wouldn't go wider than 38. Remember, it's going to be in a DSLR format, and you will have to stop them down. The maximum aperture, you know, is probably not usable, and you might have to go, you know, 2 f-stops down from what is the rating on the lens itself. You notice what I do here is I like to control the camera with an app on a tablet, and mount it to the tripod so I can pick up the whole rig and move it around. You find either controlling the camera or these little handheld controller type devices. They'll work pretty well and you'll be happy with them, but sooner or later, it's just so much easier, especially for framing and doing all kinds of things, doing repeat images, to actually use an app on a tablet. So I have two setups. In one case, I would use a DSLR, and the other, I'd actually use a cooled astronomical camera. So you are going to have power, but if you can see from the device, you can get a little intermediate mechanical interfaces like this thing in purple, or I'm sorry, orange, that will accept the M42 threads on your camera, as well as the bayonet on the lens, and people can help you get the back focus right, and they really work fine. A little bit less portable, but because you're going to have a battery for the cooling, but of course that solves the summer problem. I think this is kind of obvious. The DSLR just works. You can buy camera lenses, easy format to use. And of course, my wife is really happy if I spend a lot of money on cameras that'll take pictures of the family and the dog. Watch the lenses. Rokinon has a good reputation for coma control, but not necessarily lens-to-lens QA issues. Again, I talked a little bit about noise. I kind of like full frame, like a Canon 6D the best. And I haven't tried the new generation of mirrorless cameras, but that's probably a good option now because they seem to be very capable. I've used cool standard ZWO cameras before, but again, you're going to have to worry about the back focus for the camera lens, which is solvable. There are plenty of adapters and so forth. But then you're going to be in a FITS format rather than a DSLR format. And you probably want to play around with some specialized filters. Note that if you use a cool camera, it's not designed like a DSLR, so you're not going to get computer control of your lens aperture, but you're going to have to manually control the lens aperture. Like if you have to stop down 2 stops because your lens doesn't perform so well with coma, you're going to have to do that separately. Whereas if you use a DSLR and an app, you can just set in the f-stop that you want. You'll see tables like this. I don't actually believe all of them because this thing would say for a 28 millimeter, I can get 18 seconds on a full frame. I think you're beginning to get a little bit of elongation at 18 seconds, so I probably wouldn't go more than 11. So you're going to have to experiment with that. But that's the nature of what you're going to be doing. You're going to be doing well under 30-second, well, probably under 15-second exposures. You can stack, but remember, if you're not tracking, then you're going to have to separate the foreground from the sky that you're tracking, do a composite of the sky background, and then bring it back in and have to worry about, concealing that little bit of area that's kind of hard to mend. Obviously, but if you can track, then your longer exposures are only limited by sky glow, and you can improve the signal to noise tremendously over single exposures. So I think that's for constellations. You can track with your mount. You can go piggyback if you already have a telescope with a mount. You can install your camera with a piggyback kind of arrangement, and just use your great big old SCT as the guide camera. Or you can buy these special guiders, but I kind of recommend, if you're really going to do this and get into it, I'd probably buy an inexpensive tracking mount and go ahead and spend the money, like a GEM 28 or something like that. They'll probably give you better results. I think that's all I have. But in summary, what you would do if you go back to some of these images that I showed you is you'll have your rig on a tripod, and you're going to be framing a foreground object and the stars, and you may have a preconceived notion of what it might be like, but you're going to take some images, you're going to move around, you're going to change, because you're changing the light that you're playing on the foreground object as well as the composition within the sky. So it's kind of fun, it's creative, but again, of course, you don't get the deep sky objects that other people are going to be taking. So I'm going to stop and turn it over to the next speaker.
Scott Dixon. Scott's been doing exoplanet work for quite a long time. I'll go ahead and bring up his presentation. Scott, turn it over to you. Scott would have to unmute his microphone first.
There, now maybe I will be better heard, I think. That's good. Let's see, for a number of years, I've been involved in doing some astrophotography that involves, that works on science or is involved in science, and exoplanets is certainly one of those things. Dave, can you go to the next slide? Yeah, and I don't know how much everybody here knows about exoplanets, but the first ones were detected pretty recently in the 1990s. And there are more than three, but there are three basic ways to do that. One is when the exoplanet transits in front of its star, you can see a dip in the light. You can also measure with a spectrometer. You can also measure the radial velocity of the star that is caused by the planet, because the star and the planets don't really orbit around the stars. The stars and the planets orbit together around their center of mass. And then, of course, there's direct imaging. And of those three techniques, the one that amateurs can get involved in is the transit method. For a planet to be seen in the transit method, the plane of the planet's orbit has to be basically edge on to the Earth, so that what you're seeing is kind of what you'd call an eclipse of the if it were a planet in our system, we'd call it an eclipse. And it's because of that geometry requirement, only a very small fraction of all the planets up there can be detected by the transit method. But there's so many planets that even though you only get a small fraction of them by the transit method, you get a whole lot of planets. So, and this is something that we amateurs can do. And a little bit of history on exoplanet detections. The Kepler satellite lasted 3.5 years, and it stared at one small field in the summer Cygnus, in the summer constellation Cygnus, for all that time, and looked for dimming in the stars as planets transited in front of them. And there were a large number of stars there because it's near it's in the Milky Way. And many of them were quite dim, down to magnitude 14 or so. And Kepler actually detected 2,600 exoplanets were confirmed. And they did their confirmation all by themselves. There was no opportunity for amateurs like us to get involved. But the current satellite that's up there and working very well is TESS. And TESS is basically 4 cameras. If you look at a picture of it, it looks like a DSLR camera with a nice big lens on it. Of course, they're tailor-made and custom cameras, but there's 4 of them, each with a 24 by 24 degree field of view, so they can cover the whole sky, and are aimed at much brighter and closer stars, so that the exoplanets transiting these stars are much more detectable by even small telescopes. And to date, there have been up to 6. There have been, by TESS, there have been 6,000 planet candidates detected. But because of the TESS field of view, because they see a dip in the light curve around one star, they aren't convinced. They aren't confirmed planets. In order to, so there could be other things causing the dip, and TESS needs confirmation of these exoplanets, and that's the sort of thing that amateurs do. So the next slide, Dave. Dave, there we go. So did you skip a slide? Go back, yeah. Oh, so what an amateur needs to do to observe an exoplanet transit, the skills and equipment that you require are not a whole lot different than what you do just for deep sky imaging. These transits are several hours long, and you need to observe before and after the transit, and take a series of images that cover that period of time. And then from those images, you need to do very good photometry. Because the skylight from the planet transit is only dimmed by a fraction of a percent, less than, often way under 1%. So it needs to be very good photometry with calibrated images, and you have to be careful not to let your star be saturated. But the equipment and knowledge that amateur imagers have is basically all the equipment that you need to do these exoplanet transits. But the part taking the pictures and getting the data is just a small part of the whole process. Once you have the images, they must be processed to get the light curves. And that is certainly something we can do as amateurs. Next slide, Dave. So how can we do it? What are the things that we need to know and the mechanics of it? First of all, supporting the TESS confirmation process, where they're trying to confirm that one of their candidates is really an exoplanet, is not at all an easy process. I think you need to start doing observations of transits of known planets, known exoplanets, before you get into trying to confirm TESS candidates. In order to do that, you need to be a member of what's called the TESS follow-on program subgroup 1, which is basically small telescopes seeing limited photometry to confirm that their candidates are really exoplanets. And it involves a piece of software. To do the photometry involves a piece of software called AIJ, AstroImage-J, and there's a learning curve associated with AstroImage-J. It is not simple or easy to learn right away, so that isn't probably the way it would start. But follow-up observations of known exoplanets is quite doable. And there's this site at the Swarthmore College that has, if you go to that site and on any particular night, you will see all the candidate and put in your location into the site, then you will see all the exoplanet transits that may be visible during that night or any future nights you want to look up. So you can get all the information that you need from the Swarthmore site in order to take observations of those transits. And the other part that needs to be done is once you have the observations, you need to do the photometry to get the light curve. And JPL has developed a code that's called Exotic, which is very efficient and effective in generating the light curves that you need to evaluate the transit that you've observed. And that Exotic can either be run online or you can download it and run it on your machine. But it really makes the process of exploiting the images that you've collected a whole lot easier. And then once you have actually generated the light curve, the AAVSO, Amateur American Variable Star Observers has a database where you deposit that, and then it becomes part of the science database of exoplanet transits. And there's different ways you can do this. You can, of course, do it with your own equipment. For years now, we've been using the SDAA's Taro Observatory to do these observations. And there's an organization called BRIEF, run by Pat Boyce. He's one of our members. And he does a lot about exoplanet observations, and he would certainly like to help you in doing that. And me too. I mean, I'm happy to chip in and do what I can. To anybody that's interested, I'll tell you exactly what I know. And that's about all I have on exoplanets. Dave, do you want me to say a little bit about Speckle too?
If you can, sure.
I don't have some charts on it, but Speckle imaging is also something that amateurs can do. It's a little more complicated and difficult, and I don't think that if you're starting out that's where you should start out. But as you probably know, most of the stars in the sky are actually doubles or triples or multiple star systems. And many of them are so close together that they look just like a single star to us when we look at them. And it's important to observe these doubles in order to understand their orbits around each other. And from the orbits, you can infer things about their mass and the interaction between the different stars. But when they're very close together, you can't resolve them because the atmosphere blurs the image. So there's a technique called speckle interferometry that basically freezes the atmosphere, and using a bunch of math is able to take out the blurring effect of the atmosphere. And basically with speckle photometry, you develop you have to have a system that has very high resolution. That is, the plate scale of your images needs to be on the order of 1/10 of an arcsecond or so. So the equipment that you use to do just deep sky photometry is probably not what you need. You need, in addition to that, you need a Barlow lens to magnify the images to get the plate scale down to 1/10 of an arcsecond or so. And so when you have done that and you take Then what you do is to take a series of images, perhaps 1,000 of them, that are each on the order of a few tens of milliseconds long. And so each of those 1,000 images freezes the atmosphere and allows you, when they're combined and you do some Fourier analysis on them, allows you to take out the effect of the atmosphere and see very sharp images of the double star, so that you can measure the separation and rotation angle of the double. And from that, then you can, if from a series of those observations, then you can measure the orbit around of the two stars around each other. So this is another thing that you can get into, speckle photometry. Don't recommend it as your first experience, but as you move along, you may well get interested in doing that as well. And I think that's more than I have to say, Dave.
Scott, we have a question in the chat window from Aziz. And
Okay.
he asked, how far can we reach for exoplanet searching? Assumption is the area of the universe that is accessible for this search limited to the vicinity of a solar system. Can the Milky Way's distant parts be observed for individual stars?
Yes, and I think as long as the star is, the magnitude is bright enough for you to get a good image sequence on it, then you can observe it for an exoplanet, and that will largely cover most of the galaxy. Probably not in other galaxies.
All right. Mr. Dave, you want to take it from here?
Yes, I think I'm going to share here.
You might have Cindy turn off her speaker because it's feeding back into your microphone.
Cindy, did you get that? She got it, yes. Thanks, guys. It's been pretty interesting for me to hear all of these things. Scott, thank you a lot for hearing another explanation of some of the things, especially the speckle stuff, which I don't really know much about. But anyway, let's move on to spectroscopy, another tool that we have in the tool shed. And this particular image here is a picture of the spectrograph that I'm currently using. Here's the general view of it over here on the left. It's a C8 telescope, standard old-fashioned, with 3 cameras on it. It has a science camera, a guide camera, and a what I call an electronic finder camera. And this is my new mount, the AM5, which I'm having a lot of fun with because it's very light and easy to carry around. So that's kind of nice. Over here on the side, the right picture here, this area, I don't know if you can see my cursor or not.
Yeah, we can see it.
Yes, you can. Okay. This section right here is the actual heart of the spectrograph. It involves a grating and a prism. We call that, put it together, it's called a grism, and a couple of lenses. It's called an ALPI 600. It's a low resolution spectrograph. It's made by a company called Cheliac, which is French. This box right here is an off-axis guider. And of course, this would be the guide camera. This has a small mirror in it with a tiny slit. The slit provides the slit part of the spectrograph here. This box here, this white box, is a calibration unit. It has a railcoat lamp to provide calibration lines for the spectroscope. And it also has an incandescent lamp in it for creating flat field images. So it's all engineered so that's one unit, and it engineered so that it creates a nice flat field and nice good images for calibration. So that's the the basic spectrograph that I have put together. I've had several spectrographs that I've built myself, very simple, inexpensive, using prisms and gratings. We call that a grism. And later on, I think I'll show you one of the spectra that I got with last year with one of those devices. It's not too hard to do. It's just like playing with the Tinker Toys in a junk box. You pull a bunch of stuff together, put it together, try it out, get it to come to focus, and see what you get. And it's been a lot of fun to play with that. But last year I ended up spending a little bit of money and bought this system here so I could move on and improve my my game here. So that's a spectrograph, but I want to say it's very simple to see a stellar spectra. And the most common version of a stellar spectra is a rainbow. So in a rainbow, the light source is our sun, obviously. And the spectral dispersion method uses ice or water droplets in the clouds. And it projects a rainbow of colors onto another section of clouds. And then the recording media is your own eyeballs, your own vision. So that's a pretty good example of a standard spectrum and a way to look at it. It does the same exact things that my spectrograph does. It just does it in a very simple way. So thinking about a natural spectrum, during the daytime when the sun is fairly high in the sky and it's fairly bright white, the sun looks pretty bright, mostly white. It's actually a mixture of colors. We've heard this many times. It's a mixture of wavelengths of light. And it all comes together. Our eyes say that it's bright white, but we know that it does involve lots of different wavelengths and frequencies. So the spectrograph takes that white light and breaks it up into composite colors or bands, very narrow bands of color. And that's basically what a spectrograph is. So my spectrograph here, I've already said, it's a classic C8. It has an f6.3 focal reducer here. The LP600 spectrograph here, off-axis guider, the calibration lamp. I'm using an ASI 183 monochrome camera, and my new AM5 mount. So that's kind of fun. So here we have getting down to a basic concept of what a spectrum is. Why is it important for us to differentiate the brightness or magnitude of a star and its color? So the two things you look at when you look at the sky, a night sky with just your eyes up there, stargazing around, you notice lots of stars and they have different brightnesses. And we call that a change in magnitude, which most of you know. And the process of capturing the brightness of a star is what we've just been talking about with Scott, and that is photometry. But often you look at Betelgeuse or Antares, and you see that some stars have different colors. Even naked eye, you can recognize that some stars are reddish or orange or cream colored as opposed to blue. So that color involves a change of wavelengths, and the science of studying that color is spectroscopy. So I'd like to say, Ken, I'd like to say thank you very much for showing that video. It was interesting, the Caltech video talked about the use of photometry to realize that there's something going on with that star, and the use of spectroscopy to understand the difference between the hydrogen and helium wavelength. So that was kind of a cool introduction when I saw that thing. Is kind of a cool way to go. So this
packed a lot into that 1 minute.
Yeah, yes, it was packed a lot. I've heard a little bit about that star, but I haven't gone to research it yet. It sounds like an interesting thing to research. So I'll have to follow up on that. Yeah. So we have this thing here called the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram was initially conceived in the early 20th century, and it involved a concept where they're combining these two kinds of science we talked about, photometry and spectroscopy, to understand something about stars, to create a scatter plot diagram that helps the scientists understand what kind of star they're looking at. So here on this diagram, we see along the top, we see the spectral class. OBAFGKM. Pretty famous. Everybody knows about, pretty much everybody knows about spectral classes. O being very blue, very hot stars, M being very red and a very cool star in temperature. And this spectral class was first conceived by the computers at the Harvard Observatory, mostly Annie Jump Cannon and her associates. And they put together this, what became the basis for modern spectral classification. It's still used primarily today with a lot of extensions. And so it's very important to understand that that's where it actually came from. I'm not sure if you can see the bottom of this slide here, but across the bottom you see temperatures. And these temperatures involve the color of stars. So very high temperatures like 30,000 Kelvin, it'd be like O stars, and very cool temperature, 3,000 Kelvin would be towards the M star classification. And so what we see is across that horizontal portion there, we have temperatures, and the temperatures create different light, different colors of light. And so that's one of the main, that's the horizontal axis of the Hertzsprung-Russell diagram. On the left, we see something called absolute magnitude, which is brightness. So going back to what we've talked about up here, the vertical axis here is brightness or magnitude, and the horizontal axis is color or wavelength that comes from spectroscopy. So this diagram, which is used by almost all scientists involved in astronomy, takes the product of these two sciences, these two skill sets, and puts it into a combined way to understand something about stars. The idea is to take a star, measure its spectral output, its basic temperature, and measure its brightness. And the temperature versus brightness puts it on this chart somewhere. So if it's really a bright, I mean, if it's a really bright star, it'd be way up high. And if it's a really blue star, it'd be on the left. If it's a red star, it'll be on the right. So stars are placed on this plot. And it turns out there's a thing area here called the main sequence. Right? It looks like a little snaky river going through the middle of this chart. It turns out a very high percentage of standard stars fall somewhere on this main sequence. So if we chart 1 million stars, we'll find that a whole lot of those stars will end up somewhere on this chart when we take its temperature and its brightness. So it's an interesting concept. It means it's sort of a regular star. And in terms of science, it means generally, if it's on the main sequence, it has a core which is still fusing hydrogen into helium. So the main thing about the main sequence is that the core is fusing hydrogen. And that's where most stars, most general stars, somewhere fall on this plot. Now, as the star ages, it will move along this path somewhere, but not necessarily on the path. It will move somewhere on the diagram. Often it will follow this path for a ways, and then it will jump off the path and go up into the, what we call the giants or subgiants up in here. Or it may come down here into the white dwarfs and end up down in this area here. Our sun, right here in the middle, is about as average as you can find as far as stars go. It's a G2V star right in the middle of the classification at about 5,500 Kelvin temperature on the photosphere, and absolute mag about, what is it, maybe 5, something like that. So that's where our sun is today. It will be moving along this path a bit. At some point in time, when it begins to run out of hydrogen, it has to move off this path because the hydrogen fusion will slow down, maybe even stop. And this will move up probably into the giant area, become a red giant up in this area, eventually move around over here, and eventually drop back down as a white dwarf, and probably, most probably, become a planetary nebula. So we talk about the evolution of stars. This path helps us to understand, you know, what that thing is. Okay, let's get to something a little bit more interesting here. So This is an example of, if I can show you here. Up here in the top, it says 2D spectra. This bright line across here is the kind of image that I capture with my spectrograph. So this is a raw spectrum, the way it comes right off the camera as a FITS file stored as an image. And you can see it has bright areas and dark areas along this streak, okay? This, in fact, is the spectrum of the star. Now, the camera I'm using uses a monochrome. It's a monochrome camera because we get a nice clean data off that monochrome camera, and we don't need to see the color to understand what these wavelengths are. Seeing is a function of the eyes, not of the camera itself. So we use a monochrome camera. This is what the spectrum looks like here. Now, when I process that spectrum, run it through my software, and to find out exactly what the spectrum is, we end up with a 1D profile down here. So this is the spectrum that, after I finish processing the spectrum, this is what it looks like. This is a star called S Corona Borealis, which I've been tracking for a while. And as you can see, this is the blue end of the spectrum down here. Here's the red end. We're at about 3,800 to 4,000 angstroms of wavelength here, and we're about 8,000 angstroms up here. So you can see how this looks here. The curve goes way high at this end, which means it's a very red star, sort of like a Mira or a late M star, something like that. So we know that that's the general characteristics we can learn about S Corona Borealis by looking at this spectrum. Now, I wanted to explain that the wavelength is down here at the bottom in angstroms, low wavelength, long wavelength. Over here on the left, we have a thing called relative flux. So what this means is flux is sort of the energy profile that comes from the star as far as its intensity goes. So the higher the flux, the higher the intensity of the energy. And this is in relative flux. These numbers mean actually nothing at all because it tells you the percentage or the relative height of these peaks. Absolute flux is a much more difficult thing to calculate. I am not doing absolute flux at this time, and that's actually in ergs per square centimeter or something per time. And it's a lot more difficult to do, but something that professional spectroscopists would actually accomplish. For the amateur, relative flux is the usual thing. Relative flux means how high is this peak, how high is this peak, and this one is like 5 times higher than that one. It doesn't tell us how many ergs, it just tells us this is higher than that one. So that's what this scale is over here. So that's a 2D spectra, means 2-dimensional, that's the picture. 1D means it's a graph or a profile. So here's another spectra of a star called Delta SCO, and it is a multiple star, 2 or 3 stars at least. The main star is listed as type B014, B04, and type B star, remember the O, be a good girl, kiss me thing. The B is the second letter in that alphabet. So O is be the hottest, B would be the next to the hottest star. So as you can see here on this spectra, we have down here at 3,800 angstroms, we have a pretty good flux listed up here. And as we increase our wavelength, the flux drops down at here. So we call this line, we call that the continuum or the basic profile of the star. In very hot stars, this continuum is fairly easy to see. But in cool stars, you can see with a zigzag line here, it's very difficult to see. So we don't trust the spectrum profile as far as the actual line goes on these stars because they're too scattered and they're too influenced by atmospheric extinction in our during the imaging. So let's see here. So here we are again. What you see in here is we have dips in the line that drop below it, and we have a couple things, points on the line to go above it. So the dips in the line have to do with absorption. So it means that there's a light curve here as light is being generated and something absorbs the light like a filter, takes light out. at certain frequencies, and it creates this dip below the continuum. Down here, we have a peak, we call it an emission line. Emission line is a particular source of light creating some kind of energy at a very particular wavelength. In this case here, these two emission lines here are part of the hydrogen Balmer series, hydrogen alpha and hydrogen beta. Very, very common emission lines in many stars. And what we see here is light is being emitted because some part of the atmosphere of the star is being ionized, and it's creating, atomically creating the light that we now see as an emission line. So these are all things we look at very carefully concerning the analysis of a particular star. This dip down here, right at the end of the this thing, we'll see another one here, is it's called a telluric line. A telluric line is an absorption line created by Earth's atmosphere. So down here we have a lot of oxygen that always shows up in the same frequency at the same wavelength on just about all spectrum, because the light coming from the star has to pass through our atmosphere. So if we're going through a lot of atmosphere, for example, we point the telescope low to the horizon, we will see that the telluric lines of the atmosphere has a huge effect on what the overall spectrum looks like. And quite often we use these for wavelength calibration, but for good science, we often remove those lines to look at the continuum by itself. So we started out talking about a simple spectrum to see using light source of the sun. And here is a spectrum of our sun. In this case here, our sun is a G2V type star. Remember, I didn't say it before, but V is the middle of the luminescence line calculation in the spectral star type. So all those stars on the main sequence we talked about in the Hertzsprung-Russell diagram are usually a V-type star. So this is a G2V, which means it's colors G, and it's progressing into phase 2 in the G scale, and it's still burning hydrogen in the core. The red line is my spectrum, and the blue line is a reference spectrum that we use for calibration. Now, in this particular case, there is a correction that we make, instrument response correction or atmospheric correction that we make to adjust this line here to make it fit this line here. And I have not applied that correction to this spectrum, so you can see that the reference spectrum doesn't fit this way, but I'm showing this primarily for wavelength calibration. So when we do wavelength calibration using that calibration module on my spectroscope, it should line up these emission and absorption lines laterally, right and left, to make sure that the spectrum is in the same scale. Down below this spectrum, the sun, we see an actual color version of the spectrum. And we can see the colors, blue on the left side. This is sort of green in the middle, and red would be way off to the right out of the vision here. But we can see these lines, a dark line here, which matches up with this line. We see a dark line here, which matches up with this line. These are absorption lines. So light is being absorbed by something at this frequency, and it creates a dark line in the spectrum. Here's two side by side, two lines right here, and that shows you what the absorption line looks like. There's a star, T Corona Borealis, which I've been following for a while now. And this is a spectrum I took of T Corona Borealis in August of 2022, so a year ago. And T Corona Borealis is a type M3, which is a medium type M star as far as spectral classification goes. But this is interesting because it's actually classified as a recurring nova. So at certain times in its career, in its lifespan, it has had like a nova explosion, and it gains in magnitude tremendously. it turns out that this major change in photometric measurement from magnitude 2 to magnitude 10.8. Let me repeat that, magnitude 2 to magnitude 10.8. And if you know what magnitude means, that's a huge change in the amount of brightness of the star. So this recurring nova has a major period of about 80 years. And the last occurrence of a major event on T Corona Borealis was in 1946. So we're looking at another recurring of this major nova possibly in the next few years. And so we're taking a good look at this. So last year in August, I captured this spectrum. Interesting thing about this spectrum is we see this is hydrogen beta, here's hydrogen alpha emissions. And remember, we talked about relative flux, the difference between the continuum and the absorption or the emission lines is what this represents. So what we have is hydrogen beta and particularly hydrogen alpha are tremendously much larger than the baseline curve of the star. So when we're looking at the relative flux, we're saying, my gosh, it's got a lot of hydrogen alpha emission, a lot of hydrogen beta emission, which means that's ionization of some portion of the star creating that light. So that was pretty interesting last summer when I, myself and many others took this spectrum. But it's pretty clear here how much the difference is between the height of this particular feature and the baseline of the star itself. Here's another picture of T Corona Borealis, recurring nova, that I took about a month ago, July 21st of this year. Here we see hydrogen beta is almost just barely seen above the main continuum of the star. Hydrogen alpha is just a little bit above the continuum of the star. And it's a tremendous change from what it was a year ago. So here's last August, and here's July. And you can see that the kind of changes that we can record with a fairly low resolution spectrometer, and you're wondering, what's all this change? Well, all of the things that we can measure in the spectrum tells us about the star. And without going into it in this introduction here, it helps us understand the physics, whatever's happening in that star and what may be happening down the road. But we know that not only does T Corona Borealis have an 80-year cycle of a recurring nova, but it also has other cycles. It has like a 10 or 11-year cycle. And during those cycles, these changes that we're seeing, these changes that we're seeing here, like this, tells us that last year, this was in a pretty good emission was happening. And this year, those emissions have dropped down to almost nothing. So we know that it's in a sort of a period of quiescence or being quiet, getting ready for another round of whatever's going to lead up to the main 80-year cycle nova. So everybody's keeping a good track on T Corona Borealis because we don't know exactly how that's going to happen. So that's just a good example. So getting started in spectroscopy, it's a wonderful citizen science. It's a great partner for the guys doing photometry. Photometry, of course, has at least 100 years of fantastic data. AAVSO is a great organization, and they have all of this historic data that is extremely valuable. Probably nobody else can go back in the 30s and the 40s and pick up photometric data regarding stars like we can with AAVSO. And about 10 or 12 years ago, the AAVSO started a new project called AV Spec. So it's a spectroscopy aspect of their database. So that's what I'm involved in now. To get started, I started out with just a star analyzer, which is a simple grating and a DSLR camera, play around with it. Your basic imaging equipment and processes are very good skills to start with. I used a piece of software called RSpec, which there's a small charge for it, but it has a very good user interface and helps you learn a whole lot. So you need to go to AAVSO, check out both the photometry pages and the spectroscopy pages. Here's a link for AAVSO if you don't know about that. And I'm going to show you one more thing here. I think I can do this. Try this. Let's see if I can get this. I might not be able to. No, I can't do that. It's too hard when I'm sharing. So anyway, let's. I have to go back to 100. There we go. Okay, down here in the corner, Betelgeuse. Somebody we had some mention about Betelgeuse earlier. Betelgeuse in late 2021 went through this phenomenal dimming experience. And if you were looking at the sky and looking at Orion, you realized that all of a sudden Betelgeuse is not near as bright as Rigel. And it's like, wow, I mean, naked eye, you can just tell it's a lot. It's not near as bright as it used to be. And it was quite the talk of the town. Why is Betelgeuse, looking so dim? And of course, there's lots of theories and lots of science going on. Just wondering, like our presentation up at JSF, where it's talking about how long will it be before Betelgeuse goes supernova. And that conversation has been one that's pretty common. But a lot of amateurs looked hard at Betelgeuse in late 21 and 22. This down here in the corner is a spectrum of Betelgeuse that I took in, I think it's March of 22. And again, you can see the red curve is my spectrum. The blue curve is the reference spectrum used for calibration. And I compared this spectrum with spectra of Betelgeuse taken the year before all of this new things happened. The amazing thing was the photometry folks are looking at the magnitude of the star, and it had changed tremendously, big, huge changes in how bright the star was. And the spectroscopy folks are looking at the spectrum and they're saying, well, the spectrum is dimmer, but it's pretty much the same spectrum. We found that there isn't a lot of changes in the emission absorption lines, or the basic curve of the spectra during that time period. So that kind of evidence done by the scientists examining these things led them to understand or to believe that there wasn't necessarily a major change in the star itself, but that the dimming, the photometric dimming of Betelgeuse was caused by some kind of a cloud or some kind of gaseous state that was interfering in the light path. Something possibly in orbit around the star, something passing in between that caused it to be very, very dim. But when you looked at the light itself, the spectrum had not changed very much. So that was a very interesting project for guys doing photometry and spectroscopy, working together, trying to figure out a puzzle on how, what's happening with these kinds of stars. So anyway, that was sort of a little extra thing I thought I'd give you guys today. And I think that's about all I've got right now. Please call me if you have any interest or questions about doing amateur spectroscopy. I only have a couple of years in this, but I'm having a whole lot of fun. So thank you very much. And I will.
Hey, Warren, you had a question here. You put up on the chat. You want to ask that to Dave?
Yeah, Dave. So when you see those spectrums, so obviously a lot of that's going to be black body radiation. So and you see that clearly in your graphs there. But for example, in that first one, what accounts for that sawtooth then look? So you see, I can see the hydrogen alpha and the hydrogen beta. So that's understandable. But what's accounting for that?
Yeah, I don't have a very good science answer on that, but in general, a black body radiation is different than the surface of the star. We are looking at the photosphere of the star, and from that photosphere, we determined lots of things. But if you're looking at just the photosphere of the star and nothing else, it kind of looks like a black body radiation. The temperature, the higher the temperature, the more blue it is, and the strength of the spectra is off to the left. The warmer the star is, or excuse me, the cooler the star is, the more flux you see in the red end of the spectrum. So it's a general way of looking at it, and we use that as part of the analysis. But a star is not really a good emission of black body radiation. So black body radiation is really more of a laboratory process, and stars don't fit that too well because they're very complex, they have many layers. So to answer your question, blue stars, very hot stars, resemble black body radiation better than red stars and cool stars. The cool stars, what happens is, and I don't know all of the physics involved, but those sawtooth kinds of things are bands of titanium oxide and silicon oxide, and it causes these bands. And I don't really understand why the bands are created, but what happens is it disguises the actual continuum of the star. So it's very, very difficult to see the color temperature on a red star because it has all of these seesaw bands in it. And so that's a very quick answer to your question, but I don't know the physics behind the TIO band heads, but they're very well understood and very well known to guys doing hands-on spectroscopy. We know that they're there. So within those bands, we look for emission or absorption lines to use for calibration. And we try to ignore the bands a little bit, unless that is the purpose of your study. But so the basic answer to your question is the photosphere of a star is not a very good example of black body radiation. It's more of an example of it in a hot star than a cool star. Does that help? I hope.
Yeah, I'll maybe have a conversation with you offline.
Sure.
But yeah, thank you.
Anybody else? Spectral emission due to Wien's law, and then what accounts for peaks?
Yeah, that was me, and
Yeah.
I'll have that conversation.
Yeah.
with you.
Yeah, we'll have to talk offline, and I may have to do some research to answer your questions. Anybody with another question for a simple 2-year-old spectroscopist here? Okay. I think it's back to you, Dave.
Yeah. So as everybody's seen, there is a wide variety of activities that can be done with amateur telescopes. I see lots of folks here, Ross, and AC Wood and Ken, and a lot of folks who have discovered the real meaning of a black hole in space is that giant empty black hole that sucks all of your money as you get involved in this hobby. So, but everybody here will give you all of the advice. That's the good thing about ASIG, is that it has always been a great place for people to share ideas, thoughts, processing ideas, things along that line. But let's say that you don't necessarily want to throw your life savings at any of this until you actually get a feel for it, because you'll notice that everybody that's talked about equipment, there's two sides to this game. There's an equipment side, which is you go collect all of the gear and you stack it all together and you learn how to guide and all that good stuff. And then the other side of it is, I've got to learn some pieces of software to make this stuff good. So given that there's two sides of this thing, let's say that you'd just like to see if you could actually make things work. And when I say make things work, process some pretty pictures. Let me introduce you to the SDAA Tarot Observatory. Tarot Observatory, we had a club member whose name was Terry Arnold. Terry Arnold was a longtime astro imager. He was a longtime club member, and decided to make a donation to the club worth roughly $130,000. This included a lot of different telescopes and cameras and all sorts of things. But one of the things that he really wanted to make happen was a telescope that could be used for science and a telescope that could be used and collect data for people to be able to work and use and process. So this is the Terro Observatory, the Terrestrial Remote Observatory. It's just an absolutely, the gear, we actually pulled almost all of this gear off the roof of this house that was located on 2nd Street in San Diego when he decided to donate this to the club. So he never got first light on it. And unfortunately, Terry passed away in November of 2014. So Terry wanted this put together by the club. And what we've done is that we've come up with a way for club members to access, to get access to data. Oh, where to go here? To get access to club, to get access to extremely good, high quality data. Let me do this real quick. So the idea of ASIC, or of the Terrestrial Remote Observatory, is to give club members access to very high quality deep sky imaging, photograph and photometric data. As mentioned, the observatory itself and all the imaging gear for it was donated by Terry. The equipment list, now that last picture you saw contains the instrumentation on Terro is a Deep Sky Instruments 14.5 corrected RC. Deep Sky Instruments was backed by a very famous mirror builder by the name of Paul Jones. Paul was the one that actually reground the mirrors for the Lip Observatory when it came time to clean that up and refigure the mirrors. So Terry actually spent some extra dollars and the mirrors in this observatory on the DSI are actually quartz substrates. And these were personally ground by Paul Jones. The camera on the back of that telescope is an Alta U16M. It's a straight monochrome. It's got a huge chip in the thing. It's a 16803 Kodak chip, KAF, and so it's very large frame. There's an apogee filter wheel attached to it that's 10 position, and it has a full set of LRGB plus some very narrow S203 and HA filters that are all set for 3 nanometers. Terry's idea when he put this all together is he was going to do narrowband imaging from downtown San Diego. He wanted to do science and research from downtown San Diego. It's all mounted on a Paramount ME. And what we've done is we've made it completely automated so that the observatory runs on its own every single night that the weather cooperates. So what can you do as a club member? So any basic or contributing SDA member can request target data from Terra. And there's on the website, you'll find on the SDA website on the Terra specifically webpage, you'll find a form to request that you can click to fill in to request imaging data for any particular object you'd like to try. Both myself and Jeff Herman, they are the observatory managers, and we will gladly help you put together a target and recommend good target on how to frame it up to make this go. Typically we put someplace between 20 and 30 hours into each image. As I said, this is extremely high quality data, and it just produces remarkable images. Why would you want to do this? Well, the idea, as I mentioned before, is that you've got both hardware and software that you've got to learn. The nice thing about using Terra data is that you get extremely good high quality data to learn how to process. And there's several different pieces of software. Most everybody here will talk to you about PixInsight, which is a very dedicated piece of software for astroimaging processing. The learning curve for that looks like a cliff with an overhang. There's a couple of other pieces of software that will also do the same thing, although not quite to the same precision. But the data from Tarot will give you good, clean data in which to learn the art of astro image process. And it truly is an art form. There's also an archive that we've been keeping that you can have access to. It's the Tarot Data Archive, and that archive contains about 4 years of extremely high quality data. That data has been divided into two different folder types, if you will. One is it's the complete data sets, which means it contains the darks, the bias frames, the flat frames, the data frames, everything you need to start from ground zero. And if you're going to learn the tricks of image processing, this is a good way to start. The other half of the data, it's about 30 objects, are actually just the combined master subframes. So these are subframes that have been combined, calibrated, that you can basically skip all the calibration stuff and go right to combining and playing and making pretty pictures with. So those are all available on the Tarot Data Archive. Again, send a request to tarot@sdaa.org, and we'll be happy to put you on and give you an invite to that data archive. Right now, there's about 45 club members that have access to it, but it's all really straightforward, and the data is all up in zip files, so you can bring it down and do whatever kind of processing. Just to give you an idea, this is the type of data that you'll find in the Tarot Archive. This is the Cygnus wall in SHO. So this is done to the Hubble palette with extremely good quality sulfur, hydrogen, and oxygen data. This is up on the site. You can grab this, and it's actually this object also has a full spectrum data as well, so RGB and luminance data as well if you wanted to play with that. Likewise, this is the Christmas tree cluster and the Fox Fir Nebula. And again, this is data that you have complete access to, that you can learn the art of processing on. That's and again, it's a killer archive. From the aspect of any questions, we are as Ken mentioned at the beginning of the meeting here, we are in the process of putting together the ASIG group. This coming Wednesday, and we'll make an announcement. This coming Wednesday, a week from today, we are going to have a live in-person ASIG session here in San Diego, where we'll have a couple of club members put together a basic astro imaging setup, so that people who want to see what a good rig looks like, how to put it together, how all the parts work. We're going to do that. So our first in-person ASIG meeting will happen a week from today at 6:30 in the evening, located here in Scripps Ranch. I've got a big cul-de-sac out in front. We've done this in years past, where we had quite a few folks set up telescopes in front. So this time around, we're going to have a beginning astro imaging session just for folks who want to see what's involved in putting together some astro imaging gear. Questions? Anybody? Ideas? Thoughts? Unmute. Chat away.
How do we get the address to where to go?
I will send it out on. We'll have it send out on both the ASIG group. If you are the manager of the ASIG group's IO page, had recently sent out on how to get onto the ASIG group. We will use that a lot for communications, but we'll go ahead and announce this announce the location and time through the Wild Apricot, just to get everybody involved through our standard Wild Apricot email system.
Oh, I'm not on anything because I just joined the group last week, so I don't.
Oh,
Well, welcome to SDAA. if you've, since you've already joined the group, then what you will, if your membership is up to date, all that fun stuff, and it sounds like it is, we have an email system that comes out via our membership management program called Wild Apricot, and you will see that. So we'll give this announcement through the Wild Apricot email group.
Okay.
All right. Be good to see you here. Anybody else? No, we didn't. So I said we didn't have a Zoom ASIC meeting. There is what you're seeing, at least for last month, is a holdover from a long time ago. No one ever bothered to take out the monthly meeting reminders off the public calendar. So no, there wasn't one last month. It's just we're still trying to put things together and kind of figure out what the schedule is going to be for the ASIG meetings and such. And my guess is that as we move forward and try to open this up, it'll be, again, a lot, we'll probably do 3 or 4 live sessions per year where we'll get together and kind of share ideas, thoughts, and likewise do some Zoom sessions that will introduce members to the various different types of image processing stuff, maybe get a little bit more into what Dave Decker was showing as far as the software needed to use that on and stuff. So that's kind of where we're going with it. Mr. Sherman, you're sitting there shaking your head, doing fun stuff. You got any questions, buddy? Nice. You could unmute and talk,
There we go. Hopefully I can make the next Wednesday session. That's great. That's really a good thing.
Yeah, I'd say that the first ASIC meeting that we had a couple of months ago, I think that 50% of the individuals said, okay, how do I know where to start and can we get together so I can see what the system looks like? So that's kind of the first step in getting people back together. Anybody else?
General comment, this has been a great meeting, really has.
Oh, good. Thank you, sir. Final comments, Scott, Ken, Dave, you guys got any final thoughts, ideas, comments?
Well, the one thought that I had was me talking about tripod camera type stuff or even tracked, and us talking about spectroscopy and photometry. That's not what most of us do. Most of us take pretty pictures of the constellations and everything, detailed objects like you showed on the Terra archive. So in a way, that's kind of if we're doing a popularity curve, it would be getting set up to do things like that.
Meat and potatoes of astro imaging.
Yeah, it's creative and it's fun and it's a combination of hardware and software, like you said. But that's where most people are. And of course, there's the whole new field of being able to do electronically assisted astronomy, which is basically a live view stacking, and you tend to see that at star parties because you're not going to get the quality of 3 hours of deliberate work, but you're going to get some kind of neat stuff. And all of this is kind of fun to show to the public.
The growth and let's put it this way, you look back 15, 18 years ago when I first got involved in this, the complexity of trying to put together an imaging system was nerve-wracking, was frustrating, and I will absolutely guarantee you that at least 3 times, 3 different occasions, I swore that I was going to take my 12-inch Meade LX200 and turn it into a flower pot in the backyard. And the ASIC group was one of those things that was that helped me get going as far as, okay, what is it that I want to do with the equipment that I have? What I've seen very recently is a huge growth in simplifying how this stuff is put together. There was a discussion not too long ago about the ASI Air. It's a dedicated little computer that's got all the hookups. You don't have to put it together. You don't have to sit there and cuss and swear at Microsoft because something in Windows isn't working right. It's an integrated solution. You're looking at guide cameras that are simple to use. And the quality of the optics for inexpensive refractors has gone through the roof as far as price versus quality of the optics. That's what's really changed over the past 5 or 6 years. It's the adoption of the newer CMOS chip technology versus what was the basics of just about everything, which was CCDs. Those CCD chips weren't developed for mass consumption, hence the cost of the cameras. Just alone, the camera that sits on the back of Taro is a $17,000 camera all by itself. Nowadays, you can get extremely high quality cameras from ZWO that have incredibly low noise chips based on CMOS technology that are just astounding in the quality of the color pictures that they can take. And getting involved in one-shot color as opposed to filters sometimes is a much easier way to start producing images that you can really feel proud of. The one-shot color cameras in the past were not as sensitive. While they were easy to use, they just didn't have the quality of the pictures that you would see nowadays with the one-shot color cameras that are produced by ZWO and others. And a lot of that has to do with the chip technology, the CMOS chip technology that was developed by Sony and several other chip manufacturers to put into DSLRs. So there's been a wide adoption of the technology that's been in DSLRs for years. It's now been migrated into astrophotography, and that really is driving a significant improvement in the camera gear, and likewise a drop in cost in dollars per performance. It really is a remarkable change over the past 5 or 6 years. That's where we hope to see, and I'm hoping we can put together some folks in the club and outside the club. I mean, I expect to get some. I've been in the past been pretty successful at grabbing the attention of some of the best astrophotographers in the country who came in when we were doing this all on Google Hangouts. Hopefully, we'll be able to get some of those folks in that can talk a little bit about software, talk some stuff about upcoming hardware. So that's kind of where we're going with BASIC. Anything else? Ken, back to you, buddy.
Okay, well, I don't have anything else to say, except next Wednesday's ASIG meeting. Hopefully the weather is not going to betray us, and you will see a one-shot color camera because, Ed and I are not filter heads like some of our more distinguished a group will be. The next program meeting in September will be on Comet Madness. An astronomer has written a book about the great Comet Madness from the 19th century, and it should be a very interesting historic thing. I haven't scheduled the October meeting yet. I'm hoping to get the weather people who do astrospheric, who keep putting us off scheduling and then canceling. Hope to get them to finally explain, what we can expect from the weather programs and how we can feel confident about using them. November will be live at Mission Trails again, and that will be a gadget night. My virtual gadget night was a horrible failure. So let's try to do one in person this time. And of course, that's when you get to elect a new vice president. Yay. Bye-bye. So with that. Thanks.
I see a couple of questions. Somebody talking a little bit about, you can go ahead and unmute if you like, but Clarence, the loader scope program, you can ask for a loaner. I think somebody just put up a link. Michael Sherman just put up a link for it. But yes, we've been working on, Paul Kritzak has been working on putting together a loaner astro imaging rig, just to prove how frustrating everything can be. Anyway, so yes, you can get that loaner rig. He's been working very hard on putting together a rig that should be straightforward and easy to use. Relatively. Anything else from anybody?
I think that's a wrap.
I don't know, I'm looking at
Thank you
Ross
to
over
all.
here. I know he's got a lot to say about how much he's got involved in it.
Bob,
Wake up.
yeah,
I was just going to say thank you to all.
Thank you.
All right, guys. Have a great evening. Thanks for joining
All
us.
right. Thanks, Dave.
Thanks, everyone.
great talk on spectroscopy. Okay. You gonna pull it down or am I?
Oh, I'll take care of it.
Okay. Yeah, we got people leaving. I thought the spectroscopy part was really great.
Yep.
That was a very it was the examples.
Dave has been very excited over the past couple of years about doing that.
He
Definitely found his niche. He's been jumped on that bandwagon for a while.
no, that was very well done. The examples were very well discussed. There was a great little discussion. Photometry, yeah, didn't quite come off quite as well. You know, sometimes you wonder.
Scott's still here listening to you. So, yeah.
Yeah, I know, but I mean, in terms of, you know, what worked and what didn't work. I think when you rounded it off after my last, you know, question about, hey, most of us are not into spectroscopy, photometry, or something, or even cameras on sticks, where we're taking deep sky imaging, trying to make pretty pictures. And we're good at it. I think you pretty much rounded the whole thing out right about that point. And I think that's what most people are still trying to do. And, you know, I personally, you know, you will really wonder, the only way to do this is to kind of jump in and start, you know, buying your own equipment and learning how it works. I'd hate to spend all this time learning how somebody else's equipment worked and then have to do it all over again. But anyway.